Okay, so we have gone through thus far steps 1 through 5, and now we're doing 6. All right. So this is the rule that always trips everyone up. So we're going to walk through this one fairly carefully. And so rule 6 is all predicated off of. Let's see, where is it at? Rule 6 is all predicated off of this basic definition of the root locus. So we said that on Friday's lecture, we said that the root locus is essentially given by this equation that the root locus is the values of s such that g of s is equal to a negative real number, right? Coming from the definition of what a pole is. And then we said from this information we can come up with two predecessor rules of that. And so that means that the magnitude of g of s has to equal 1 over k, and then also that the phase angle of g of s has to equal 180 or plus some sort of multiple of 360 added to that. So either 180 or 360 degree rotations from 180. And so rule 6 is completely based off of this. And so what we're going to look at is the phase angles between what we're going to call the departure angle and all the different poles and zeros. So what this rule is saying is if we look at our arrangement of our system, so here's our kind of quick sketch of what a root locus plot looks like right now. All right, kind of rough and dirty sketch here. We already know the branch, associated with the pole at the origin. Not too important to this, but just trying to fill this in. And what we're trying to understand is the departure angle at which this branch of the root locus associated with this open loop pole is going to catch up to our asymptote. So we said we had these asymptotes going in this direction. And we don't know if the root locus, when it leaves this pole, originally goes in this direction to catch up to the asymptote, or if it goes in this direction to catch up to this asymptote. We need to figure that out. That's what we're trying to figure out with rule 6 here. And so what we're going to do is we're going to use this angle rule, and we're going to take a test point, S, here. Test point S. And if this test point S is on the root locus, then the angle identity will be satisfied. And so that means if the angle identity is satisfied, that means that the summation of the angles of that test point from all the zeros minus the summation of all the angles of that test point from all the poles has to be equal 180 degrees plus or minus some sort of integer multiple of 360 degrees. All right, so if we're saying that here's our test point, right, and I want to know then what is then the angle or summation of all these angles to that test point, right, to try and evaluate this right here. So what I'm going to look at is I'm going to look at what is the vector running from this pole and that test point, this pole and that test point, and then also this pole, this test point, and then I want to solve for this angle to understand what's called the departure angle of this branch of the root locus. Right. So this one trips up a lot of students. We'll go through quite a few examples of this, try and get you more comfortable with it. But what we're saying here is we want to know this angle. That means we're extracting this angle from the summation. And so another way in which we can rewrite this, we're going to pull out a single angle from here. So we're going to say that the departure angle of that test point minus our pole of interest, which we'll call Pj, has to be then equal to summation I to m angle of S minus all your 0 locations, I'm sorry, Pj. I'll talk about what that is in a second, minus summation, and then here you have to look at the index a little carefully. This is I is equal to 1, except for I, oops, extraneous lines here, not equal to j. So we're going to go all the way from 1 to n, skipping the case of the pole of interest that we're talking about. Okay, minus 180 degrees. So I've just rearranged this. What I've done is just pulled out a single one of these phase angles out of this term, moved it to the other side, then moved the 180 to the other side as well. Okay, so what this is saying is that our departure angle is the angle between this pole and its test point, and then that is equal to the summation of the pole of interest, so that we're talking about, the Pj. So this departure angle is an infinitesimal distance away from this pole of interest. So we're saying that if I want to know the phase angle between a 0 location and S, that's as good as just knowing the departure or the angle between that pole of interest and that 0 location. All right. So we're saying infinitesimal distance away, and then same thing with all the other poles. And this is going to be an equation we're going to use. I think the best way to explain this, though, is actually give the example, give this for a few different examples. So we'll have an example. In this case, we'll have a lot of other examples in this class to help you with this rule of this. So in this example, we are going to say that we care about what we'll call P1. So what I call P1, P2, P3 doesn't matter. It's just naming something. And so we're going to say that I care about the departure angle for P1 is equal to negative 4 plus 4i. All right. So that is negative 4 plus 4i is this pole right here. So I'll use green for construction lines here. So we care about P1. Right here. And so what we're going to do, there are no zeros in this problem, so the summation of the phase angles of all the zeros is going to be equal to 0. But what I'm going to be adding up is I'm going to be adding up the phase angle of the vector running from this pole to my pole of interest. All right, so this is this vector is going due north, right? So this is a phase angle of 90 degrees, and add up the phase angle of vector running from this pole to my pole of interest. This is at negative 4 plus 4i, so that's a phase angle of 135 degrees. All right, by adding these up and then comparing it to 180, it's going to then allow me to understand in what direction does this branch of the locus originally depart. It doesn't say far away what's the phase angle, but it says originally what direction does this depart, and then that'll give us a sense of a better idea of, I guess, the shape of this root locus plot. Okay. So then putting these angles into this equation here, S minus P1 is equal to, or make sure you can see the base equation. All right, so no zeros in this problem. So this is 0 minus 90 degrees plus 135 degrees minus 180 is equal to negative 45 degrees. Okay, any questions about that at first glance? Okay. Okay, so what that means is we know two things. We know that this branch of the locus will eventually have to catch up with this asymptote, and it originally departs at a phase angle, or at an angle of negative 45 degrees. So that this branch is going to initially head in this direction, but we know that eventually it has to catch up with this branch. Right? So initially going to go at negative 45 degrees. The root locus kind of has, I would say, for lack of a better term, we'll say inertia to it, and that it doesn't make any really abrupt turns, except if you're on the real axis. It kind of has a smooth slope to it, or smooth contour to it, so it's going to look something like this right here. All right, so we know it's going to break away in this location. So why this is important is that if it were to break towards the left and then catch up with the this asymptote going off at positive 6 degrees, that means that we could probably design a controller to make, just proportional control, to make the system respond in a pretty favorable manner, because we're going farther to the left, so that's faster decay rate, and we're also not, and then also we're not getting cases where we have higher or lower damping ratios. So this one's actually going farther into the right half plane. It's actually becoming more unstable as we increase this gain. If it go to the left first, there'd actually be a period where it's getting less oscillations, faster decay rate, all these other things. So it's saying it's almost immediately going to the case that you don't want. Okay, so we also know that the root locus is symmetric. So we don't actually have to evaluate the departure angle for this pole. We know it's going to always be symmetric about the real axis. But for the sake of your learning, we'll go through this example as another example to show the departure angles, just so you have that kind of as another point of clarification. So now if we're looking at what is the phase angle or departure angle for this branch, we'd be looking at the vector going from this pole, and that pole is going to be negative 90 degrees, and this pole, and the pole of interest, which is negative 135 degrees, and we should get positive 45. So this one is negative 45, we should get positive 45 because the root locus has to be symmetric. So same evaluation, we call this P2 is equal to negative 4 minus 4i. Still no zeros. Minus 90, minus 135, minus 180 should give us then 45 degrees. So we have minus 90 minus 35 is negative 225, right? Minus another 180 is going to give us 435, right? What is that? Yeah, 430. Can't add this morning. I haven't had coffee yet today, so someone help me with math there. 225, 180. Okay. Yeah. Anyhow, equals 45 degrees. Trust me. All right, so just then symmetric, and then catches up with this branch of the root locus. Okay, so if we increase the gain to be too large of a number, closed loop poles are going to move in the right half plane, unstable system. Right. All right, so that is, in terms of hand plotting this is it for this example. Any questions about what we did here? We haven't gone through all the rules. Not every single example leverages all the rules of applying this. So the next example, between the two examples, we'll get through all of them. But any questions about what we did here? Yes, Sarah. Yeah. So yeah, in terms of like rules of thumb or things we can draw by hand, that's getting in just details we don't really have too great of rules for. That we have to plot. We're going to talk about plotting this in a second.
What does K represent? So G1 of S is the controller, and that's been lumped into G of S, right?
Yeah. So this is going back. Yeah. Let's talk about that just so everyone's on the same page. Yeah, so that is this discussion here. So we said that, all right, in a system we have hardware and we have software, right? And these are physically two very different entities, right? One is a piece of hardware you're trying to control, and the other one is an algorithm you write into a computer software package. But you can write transfer functions for both of them. And so what we're doing, even though these are completely different in terms of what they would look like sitting at your desk, we're still lumping them together into a single transfer function. We're saying anything that has dynamics associated with it, we're going to lump into this parameter G. That's what we're applying the root locus for. And then K is some parameter of interest that we care about varying. Most often cases, this is going to be a proportional gain, or some scaling of PID gains, or some scaling of what we'll call lead lag controllers later. But this is some parameter of interest that we care about changing. And now we're looking at how the closed loop poles move around when we change this single parameter. Does that make sense? Okay. Like a three-dimensional root locus plot? Not really. So what we can do is we can say that the KP gain is some factor times KP, or a K. KI is some factor times K. KD is some factor times K. So you're still only moving one parameter. Two-dimensional root locus plots, you don't really see those too often. There are other tools for that more complex analysis, but it's not kind of root locus plot.
So we can't really use the PID tuning then unless we know the proportionality constant?
We'll show ways in which you can use some of these tools that we first establish the proportionality constant and then set the gain. We'll get to that. Okay, so there are some questions like how do you get, yeah, go ahead.
So is this mainly to figure out how your stability changes as you increase all of your values that make up K?
That is one way you can do this. There's a lot of uses for it. So we'll show how you can use this for design as well. So this is showing if we have a form of G of S and we're only modifying a single parameter, we'll also show how we can design elements of G of S to kind of morph the shape of this. We'll talk about how can we morph the shape of this. So we'll use it for a few different purposes. So there are some questions like how do we fill in all the details, and how we fill in details is really with software. So I showed, when we first introduced this, I showed the RL plot. I'll show another tool that I think you'll find even more useful than RL plot. Or our Locus, I guess it was. And this is a tool that will, I don't know if I would say it'll be your friend. You'll use it a lot. All right, so this is entering in the transfer function as ZPK form. So we have no zeros, and then we have poles at 0, -4, +4i, -4, -4i, and we have a gain of 1 in this case. All right, so this gives us exactly the transfer function we have in our problem. Sorry, the font is very small right now. Well, the font is not, we're not really talking about the fonts here too bad, but this is entering in the transfer function. And if I want to if I were to look at this, I say R locus. This is, like I said, the easy way to get the R locus plot is you just do R locus of G. All right, and this is essentially what we just plotted, right? So the scales are a little, they're not quite uniform, right? So this is a total scale of 40 on this side, and this is a total scale of 35 on this side, on the x-axis. So this is at negative 45, this is at positive 45, but this is essentially the root locus plot we just did by hand, but it's exact, right? Except in comparison to our approximate root locus plot. So this is one way to plot the root locus plot. One that I think you'll find a little more informative and interactive is if you use this software tool, which I just showed very briefly so far. We'll go through this, and you'll be using this tool a lot. It's called CISO tool. So as a reminder, CISO stands for single input, single output. So everything we're doing in this class, single input, single output. So if we type in CISO tool, up will pop a GUI in a second. All right. And you'll start to see some things that look very familiar. All right. Nothing in here yet because we haven't provided the GUI any data yet. But we have a Bodhi plot that's going to show up here. That should be familiar. Upper right, we have a root locus plot, which we're now learning. And then on the bottom right, we have a step response. Right? So everything we are now familiar with in this tool. Okay. And then if we want to look at how do we input information into this, we go into Edit Architecture. All right, and then as with everything in MATLAB, you have about 100 more settings than I can possibly teach you in a given class, or 100 times more settings that I can possibly teach you in a given class. So we're going to strip down all the other extraneous details. You'll see a bunch of different configurations of feedback loops, like this one. All right, all these are well outside this class. The first one is going to be your friend. This is the one you're going to use. And you'll see that also MATLAB, they have a different naming convention for their blocks. So their G is RG2, their C is RG1. Okay, but we have thus far, we have information about the plant. So we can load this from the workspace by clicking here, and we say, all right, we want G to be imported. And then we say, okay. All right, so then we have a few things. We have the Bodhi plot automatically generated for us. We have the root locus plot all automatically generated for us. And then we have the step response all automatically generated for us. So then the other thing that's interesting about this is when I showed this animation, we first introduced the idea of the root locus plot. We had this root locus plot almost being formed, and then we had the tips of the root locus plot was the closed loop pole location for a given value of k. So MATLAB uses a value of k of 1 as default to give you then, all right, let's see if it lets me grab this. There we go. Sorry, my computer's being slow today. All right, so these pink squares here are the closed loop poles for the given value of k that we have specified thus far. So if we want to know what that value of k is, we can open up the controller block here. And we'll see that by me moving around, that by basically physically, well not physically, but virtually moving around the closed loop pole, by moving around where these pink boxes are, we can see what the value of k was associated with that closed loop pole location. So if I wanted to reset this back to the default, I would type 1 here. It should move back to where we were. And then I can look at as this goes up to 10. All right, poles move a little bit. I move this up to say 100. Oops. Poles are now in this location. So you can start to observe some traits that we expect as these complex conjugate poles here, or the branches associated with these complex conjugate poles, kind of merge or go to the right half plane, and you're going to have a larger and larger imaginary part. The angle from the imaginary axis and that pole is going to become smaller and smaller. Therefore, you have a smaller damping ratio. You start to see that in your step response. You start to get oscillations in your response that we didn't see when we had a smaller value of k. And if I say move this up to 300, all right, that's right where, approximately where I crossed over into the right half plane. All right. And so if you look at the step response for the system, you see this is blowing out. This is times 10 to the 12 on your y-axis, right? So this is now, so this is an unstable system. All right. And we can try and figure out exactly where that value is. Not exactly, but close. Still not quite there. There we go. So somewhere on there, we're right on the axis. This is taking around 1,000 seconds for the oscillation to die out. Right? This is right at the cusp of being unstable. Right? So this is a tool where you can start to understand kind of where the closed-loop poles are, how gain affects this, right? And so if I dial down the gain by moving this to the right, we see we get then a response that looks a lot more favorable, right, than that. Other features here, we'll talk about, we're not quite to the point where we can start to talk about what's going on in this Bodhi plot. It's a Bodhi plot, you understand that. But there are some features here, namely called the gain margin and phase margin that we will get to. We haven't got to it yet, but that's some other information. I alluded to this before that there are factors of safety in control systems. The gain margin and phase margin are these factors of safety. We'll get there. And then also, as before, I showed that we can always put design requirements or design specifications on this plot. So for those of you who were not there the day we did this, we can say, all right, we want to have all our poles to have at least a natural frequency of, we'll say 4. And so as you've learned in this class, this is a semicircle, right? So we can look and say, all right, keep the poles outside of this region for setting our design requirements. And we can also look and see how that corresponds to design requirements in the step response. So we could say that, let's say we want to have an overshoot less than 10%. So if I put this on there, then it actually shows, all right, is my overshoot over 10% or not? Right, so we have all these design requirements. We can start to basically put markers on plots for you so you can see, all right, are my design requirements satisfied or are they not satisfied in a pretty, let's say, visual format so you can see if it's correct or not. Okay. Any questions on the kind of this introduction to some of these tools? Okay. So I showed you the long form of basically clicking on this edit architecture and importing that data. Just as a quick note, if I don't know what that is, if I don't want to insert the data every time, I just do CISO tool G. The default is that whatever transfer function is in there is the plant. And so then when this populates, it'll automatically be in there. So you don't have to enter that in every time if you don't want to. Yes?
You say it's the plant. Like, is it the plant and the controller, except you pulled out a K?
Yeah, in this case, yeah. So, yeah. I mean, so maybe I was using the language a little too loosely there. If like there is no controller design yet, so we're saying all the dynamics are associated with the plant, so I call it the plant. But you're right. In general, this would be the dynamics of the controller multiply dynamics with the plant. Okay. All right, so that was one example of some of the software tools. We'll go to the next example here. Okay, so same idea as before. We're going to plot the root locus for this transfer function. The difference here is that we have repeated roots. We have a 0 in this case as well. We didn't have that in the previous example, but here we also have repeated roots. We have 2 poles at -4, and we'll talk about how that looks like for our root locus plot. So going through, if we want to know what M and N are, we have 1, 0. We have 4 poles because we have a repeated pole at -4. And so that means our set of zeros are at, we have 1, 0 at -1. Set of poles, we have poles at 0, -2, -4, -4. Okay, so rule 1 is associated with the location of the closed loop poles at k is equal to 0. Okay, so an appropriate axes for this example, 2, 4, 6, 8. All right, and then we know that the root locus, in terms of the closed loop poles, start at the open poles for k is equal to 0. So we have open loop poles at 0, -2, and then we have a double pole at -4. So I think I said this in a recitation once or somewhere, but if we want to indicate a double pole, so if I were to say, all right, a double pole is just 2 poles written on top of each other, you probably couldn't see that I wrote 2 poles written on top of each other. So the kind of the convention for a double pole is we make this into hashtag mark here. This indicates a double pole. All right, and then we have a 0 at -1, which is here. Yes?
If k equals to 0, wouldn't the response just be like completely flat, no response at all?
Yeah, exactly. So you're saying, all right, if k is equal to 0, then we look at wherever my diagrams here, saying if k is equal to 0, then everything in terms of the error signal gets multiplied by 0, so it just gets killed, so there is no response. Yeah, so this is the theoretical limit when k is equal to 0. All right, so as soon as k is non-zero, or just slightly larger than 0, then something does pass through. You're right, it's going to have a really small gain associated with it, but it tells us how the root locus plot starts. Okay, so we have this configuration for k is equal to 0. Where am I at? All right, 2. All right, so rule 2 is about where the branches terminate. All right, and so we said that from our observations and other previous rules here, that if we have a 0, a branch of the root locus always must terminate at that 0. So that means that one branch, we have 1, 0, so we have one branch terminates at the 1, 0, right, we have 4 poles, so therefore we have 4 branches. So that means that 3 branches terminate at infinity, and we need to just now understand what direction does it go off to infinity. Okay, so the way in which we find this similar variable. All right, so we solve for all these. As we talked about on Friday, that it's purely based off the difference between the number of poles and zeros. So in this case, we have, just like the previous example, a difference of 3. We'll have plenty of other examples that shows different differences. So from the example we did on Friday, we know that the angles are going to be at 60, negative 60, negative 180 from Friday. Right? If it's difference a different number, we'd have different different examples or different angles. All right, asymptote intersection points. All right, it's given by this formula. So for this example, we have a single 0 at negative 1, right? We have then 4 poles. The 4 poles are at negative 2, negative 4, negative 4, and 0. One, 0, 4 poles. And this gives us an intersection point of negative 9/3, or what equals negative 3. All right, any questions about that? Now we had a 0 on this. Okay, so adding construction lines here. So this means that our asymptote is at negative 3. That's sigma A. We have asymptotes going off to negative 180, or positive 180, however you want to think about it. And then plus 60 and minus 60. All right, terrible. Okay, so rule 5 is this on the real axis, the root locus to the left of an odd number of poles and zeros. So, all right, so following this rule here. So I said before on Friday, I find it easiest to work from right to left. And so we look in this region, we say, all right, we are to the left of 0 poles and zeros, right? So there's nothing to the right of us. 0 is an even number, all right? So the root locus does not exist here. And then as we go and then cross over this pole at the origin, we are now to the left of 1 pole and 0, right? So we're to the left of a single pole. So it means that the root locus does exist, at least from this region. As soon as we cross over the 0, we are now to the left of 2 poles and zeros, right? That's an even number. So the root locus does not exist here. As soon as I cross over the pole at -2, I am to the left of 3 poles and zeros, odd number. And then as soon as I cross over this double pole, I'm now to the left of 5 poles and zeros. Again, that's an odd number. All right, so this is on the real axis. So we have a few of our branches figured out already. So we have one branch here, right? And this is a really simple branch. This is just, this branch terminates at the 0, right? So we know that our branches either have to terminate at a 0 or infinity, right? This one's done. Everything is done that we need to know here. Then we have another branch that's terminating at infinity at the -180 asymptote. Then we have to figure out this asymptote at +60, asymptote at -60 here. All right. So kind of as a thought experiment here, we have, of the 4 branches, we have 2 of them figured out already. And then we know that the asymptotes eventually have to catch up here. We also know that the root locus has to be symmetric. So what do you think is going to happen here in terms of the last 2 branches?
Just 2 poles are going to go to the right and then split off at that.
Sorry?
The 2 poles are going to go to the right, falling on the real axis, and
Okay.
then they're going to split off at that wherever it splits off.
Yeah. So you're saying that we have the 2 poles here, right? And so then you're saying that you're going to go here and they're going to break away, right, somehow from the real axis. So I agree, but the only thing is that, well, it's tough because this is a singularity point. Here we have another singularity point. But one of these is actually going to go to the left. One is going to go to the right, and this one's going to go to the left. And then we know it has to be symmetric at the real axis, so they're going to break away exactly the same point. If they break away at the same point, it would be symmetric anyway. Does that make sense? So yeah, so one of these is going to go left, doesn't matter which one, these are interchangeable. Both poles are -4. Right? One's going to go to the right, one's going to the left, and then break away. And then the question is at what point along the axis are they actually going to break away at? So that's another rule that we haven't talked about, that we are adding to this discussion. So we handled rule 5. Rule 6 is actually irrelevant for this problem. We don't, yes? Okay, so, yeah, so one of them has to catch up. One of them has to go to the, go along this -180 axis. So we have 2 here, right? And one has to go in this direction. That's asymptote. And then we have 2 asymptotes, therefore 2 branches that follow this. So we need 2 starts to those branches. So we need one from here and one from here.
Well, why does, like, how do you know that this one's a double X instead of like that one right there?
Okay, why isn't it this one?
Yeah, and then those 2 split.
Yeah.
I get this one.
Yeah, I don't have a great answer for you besides that the Locus doesn't do anything too crazy. So we'll say that the lack of a better terminology is that the asymptote it essentially attracts the nearest poles. Right, so this would be coming from here, or taking both of these here would be more, basically this branch is closest to one of these, so it's not going I know a better answer for you than that. Okay, so what this is looking for, this last rule, sorry, not rule 9.7, rule 7, is what's called breakaway points. This is where a branch will break away from the real axis. And what this is saying, if you look at, this is the derivative of this function with respect to s, and then we're looking at it 1 over g of s is equal to 0, or equivalent to say that the derivative is equal to infinity, right? So this actually, when we say derivative is equal to infinity, we're looking at singularity points of a system. Or the easier thing to solve is 1 over that term is equal to 0. So just think of this is looking at singularity points. Via the quotient rule, the easiest way to look at that is not in this form. This would be like the base form. If you use the quotient rule for this equality set equal to 0, and we say that g of s, we can break down and compose of its numerator and denominator. Sorry, I'll write that a little more clearly. Then via the quotient rule, this equality becomes d ds, or d, yeah. Derivative of d of s with respect to s times n of s minus d of s times derivative of n of s with respect to s, all equal to 0. Right. So for our particular example, we have that n of s is equal to s plus 1, d of s is equal to s plus 2, s plus 4 squared, which if we expand out this polynomial is this function. Okay, so now this rule gets into some pretty quickly gets into things you can't solve by hand. And so if we were to ever have a problem like this in an exam, you would have methods to do this without a calculator. But this example here, you could essentially never solve by hand. But then if we look at then what is d, derivative of d with respect to s, that's going to be equal to 4s to the third plus 30s squared plus 64s plus 32 times n of s, that's s plus 1, minus d of s, just copying below, derivative of n of s with respect to s is equal to 1, is equal to 0. All right, so I won't go through the more simplification of this. The important thing here is that we have tools that we could, essentially this is solving a fourth order polynomial, which would take me all day to do by hand. But if we throw this in a calculator, we see that the solution is -4, -2.6, and -7 plus or minus 0.73 I. Right, so fourth order polynomial, you're going to get 4 roots. So it's expression. Some of these are going to be nonsense, and some of these are going to make sense. Right? So the ones that are not on the real axis, if we're looking at breakaway points on the real axis, this doesn't make any sense, so we get rid of these two. And then if we look at, we have options of -4 and -2.6. So sometimes we'll get ones that aren't on the real are not in the locus region at all. Here we have a singularity associated with -4. That's coming from, you have the 2 poles right at -4 that break away in either direction. And then the one that makes sense is -2.6. That's the one that we're actually going to use. And so this is the correct breakaway point of the 4 that we get. So then finishing out this plot in the last minute here, at -2.6, which is right around here, the locus is going to break away from the real axis, and the other note here is it always breaks away from the real axis perpendicular to the real axis. All right, so it's going to break away perpendicularly, and then it's going to then catch up to this asymptote. So it has a little bit of inertia to it, like we talked about before, and that's going to catch up. Okay, so I'm out of time. Any questions in the last minute of class about what we did here in this example? Yes? It doesn't matter. And so, like, if we were to, just to elaborate on that question a little bit, say, for instance, we were to enter in a new transfer function, ZPK. We have poles at -1, or sorry, 0 is at -1, poles at 0, -2, -4, -4. So MATLAB is going to color code them for you. So it says that this one goes down, this one goes up. It's false coloring in terms of that point. There's actually a singularity here, and so there's no actually mathematical determination which goes up and which goes down. MATLAB is picking a direction. Yes?
If we need to know, like, what's the angle when it breaks apart, put it at like 90, but...
Oh, so it always breaks away at perpendicular to the real axis. Yeah, it's a singularity, so it has a derivative of infinity there. Yeah. Okay. All right, see you on Wednesday.